After having studied integral calculus for so long, it is time that we look at some application of the theory of definite integrals. So you may remember that we started by trying to define the notion of area of regions of this form, which are enclosed by the graph of a function y equal to fx above below by x-axis, on the left hand side by the line x equal to a, on the right hand side by the line x equal to b. And we have also called such a region or denoted such a region by rf. So you may remember that we have made sense of area of such a region by our theory of integral calculus. So let us recall the facts that we have seen before. So suppose that f is a bounded function on the closed interval a b, and suppose that it also has the property that f is bigger than or equal to 0. So geometrically this simply implies that if we consider the curve which is given by the function y equal to the equation y equal to fx lies above the x-axis when x lies in the interval x equal to a, and lies in the interval ab simply. So we say that this region rf has an area if f is integrable on ab, and in such a case we define the area of rf to be simply equal to the integral of fx in the interval ab. So let us look at some concrete examples. So the first examples that come to our mind is of y equal to x, y equal to x square. So in the first case, this is given by a straight line, and if we choose our closed interval ab in such a way that a b are both bigger than or equal to 0, then we can see that in this region, in this interval x equal to a to x equal to b, the graph of the function y equal to x always lies above the x-axis. So in particular, if we denote the function x by f of x, you can see that f of x is always bigger than or equal to 0. So then we are in the situation that we have just described above, and we can now, by our definition, you easily compute the area of the shaded region rf, which is nothing but the integral of x in the interval ab, and we have seen that this turns out to be equal to b square minus a square by 2. We have calculated this integral by using our basic definitions of UPF, LPF, etc. If you may remember, we can also derive this formula by using the second part of the fundamental theorem of calculus. Let us have a look at the next example, so which is given by y equal to x square. So if we call this function gx, so gx equal to x square, and we may easily see that in this case gx is always bigger than or equal to 0 irrespective of whatever interval that we choose. And we want to, of course, compute the area shaded in green here, which we call rg here, because we have given the name g to this function x square. So the function gx is continuous, and of course it is integrable. So by our definition, the area of the region rg, so area of rg is given by the integral of x square in the interval a to b, and we have again seen that this turns out to be equal to b cube minus a cube by 3. So now what happens if we do not have the leisure of dealing with functions whose curve or whose graph always lies above the x-axis? So what if we come up with a function which looks like this? So can we compute the integral? So we have also dealt with such a case before. We have defined the notion of signed area. We are going to define a new notion called total area, so which will give us the area bounded area shaded uh, in green in this picture. So let us recall. So in order to deal with functions which are not really non-negative, so we divide the region into two parts. So the first part consists of the parts where the region lies above the x-axis, and second part consists of the region which lies below the x-axis. So for this we made use of the two functions which are non-negative. So one is f plus and one is f minus. F plus is simply the maximum of f and 0, and f minus is negative of minimum of f and 0. So what it gives us is that in this area gets reflected by x-axis and gives an area like this. So since these two functions are now positive or non-negative at least, so we know how to make sense of these two areas. And to determine the integral, it turns out that the integral fx from the interval ab is just the difference between these two areas. But how do we compute the total area? So it may be very intuitive that we actually take area of this region, take the area of this region, take the area of this region, and sum it up. So note that in this integral, when we consider the total integration from from a to b of the function fx, this region which is below x-axis contributed something negative to the integration, but we want to take modulus of the area, the negative area, so that we are actually talking about this area which is above the x-axis. So, and that of course will give us the total area of the whole region. So what is the total area in such a case? The total area of R, if we call it R, is equal to the area of RF plus and plus area of RF minus. So as I have explained, that this exactly gives us the total area of the region. Next, let us have a look at a more concrete example. So what is a better example than to consider the function fx equal to sine x in the interval 0 to 2 pi. So we may see that from 0 to pi, the function fx equal to sine x always lies above the x-axis, and the function f always lies below the x-axis when we consider the interval pi to 2 pi. Fair enough. So let us try to figure out first. Let me try to show you what does the integration of sine x turn out to be when we integrate the function from or in the interval 0 to 2 pi. So by a simple application of the second part of FTC, you could see that the integral becomes 0. So what does it mean? So it means that the area that we have taken here, which is the area of RF plus, so this is RF plus and this is RF minus. So area of RF minus, they are equal and they have cancelled each other. So let me try to prove this concretely, what we have just said. So what is the function f plus? So what is f plus of x? See, when so so here we are actually taking the maximum of fx and so maximum of sine x and 0. So as long as x lies between 0 and pi, the maximum is of course the function sine x, because it lies strictly above the x-axis. So okay, so sine x when x lies between 0 to pi, and what happens when x lies between pi and 2 pi? So here we can see that the x-axis lies above the curve of the function y equal to f of x. So what is the maximum? The maximum is y equal to 0. So this explains why f plus x is equal to 0 when x lies between pi and 2 pi. So let me try to compute the area of RF plus. So this is the area of RF plus that we are interested in. And how do we compute? So area of RF plus, so F plus we have seen that, so f plus is always a non-negative function, so we can compute the area of RF plus. And so this is simply the integral of f plus x, and the integral runs from 0 to 2 pi. And we make use of the additivity of domains for Riemann integration. We can divide this interval 0 to 2 pi into 0 to pi and pi to 2 pi. And as we have pointed out that when x lies between pi and 2 pi, the function f plus x is equal to 0. So this integral will contribute 0 to the whole integral, and we are only interested in this part where the integral goes from 0 to pi. So as we have seen that this is equal to sine x, and by again the simple application of FTC part 2, we can see that this area turns out to be equal to 2. Similarly, when we are interested in f minus, so we can do the similar computation. You may try to do it yourself, and it is of course given here, turns out to be equal to 2. So this explains why the total integral from 0 to 2 pi of sine x is equal to 0, because after all it is equal to 0 to 2 pi area dot f plus x dx minus integral 0 to 2 pi f minus x dx, and this is equal to 2 minus 2, which is equal to 0, so which we have calculated in a completely different way. So, and what is the total area? So total area is simply the area of this region, which turned out to be equal to 2, plus the area of this region. So this region means what? We have of course taken a negative here, so it is kind of reflected about x-axis. So this is RF minus, and this area is also equal to 2, and the total area of the region which is bounded by x-axis and sine x in the interval 0 to 2 pi is nothing but equal to 2 plus 2, which is equal to 4. I hope this is clear, and this will help us in moving to our next application, where we are going to consider the area between the area of a region which is bounded bounded between two curves. So what do we mean about area of a region which is bounded by two curves? So suppose we have been given two functions, so fx and gx, and suppose we want to compute the area between the curves y equal to fx and y equal to gx. So first let us have a look at a few pictorial examples. So suppose we have plotted the graphs of these two functions y equal to fx, y equal to gx in the interval where x lies between the closed interval ab, and we want to compute the area of the region which lies exactly between this. So here y equal to gx is pictorially represented by this white line, and y equal to fx is pictorially represented by the yellow line. So you may observe that the white line does not ever come below the yellow line, and so this is exactly represented by this inequality gx is bigger than or equal to fx for all x in the closed interval ab. Similarly, we can talk about the region of region between y equal to fx and y equal to gx. So something is going to be gx, so let us call this gx as we have done here, and suppose we are interested in determining the area of this region. But now, how do we go about it intuitively? So, suppose that we know that both fx and gx are integrable functions. Does it help us? Well, it does. So how? So we know the area of the region which is bounded by the white graph. We also know the area of the region which is bounded by the yellow curve. So it is quite intuitive that the area of this region, which is shaded in green now, is actually the difference between the region which is shaded, difference between the area of the difference between the area of of the region which is shaded in white and the region which is and the area of the region which is shaded in yellow. So similar thing here. So if we want to compute this area which is shaded in yellow, shaded in white, this should be the difference of area under the white graph and the area of the region which lies under the yellow curve. So it may intuitively follow from what we have learned up to now is that in such a case, at least when gx is bigger than or equal to fx, that the area of the region that we are now concerned with, if we call this r, will be given by area of rg minus area of rf. And our definition in this case is exactly the same. By using algebra of Riemann integration, we can see that area of Rg minus area of Rf is exactly given by area of Rg minus f. So note that this is a non-negative function and we can always integrate it as we have seen above, in the previous slides. So why don't we try to consider an example. So here we are interested in finding the area of the region which is enclosed by uh, the graph of the function y equal to 2 minus x square and the function y equal to minus x. So note that this line which is depicted in yellow is the graph of the function y equal to minus x, and of course the parabola which is given by y equal to 2 minus x square, and we are trying to compute the area of the region which is enclosed by these two curves. So mainly we are interested in this region. So in such a question, we should first find out what are the points at which these two curves intersect. So let us try to find that out. So for that, we have to figure out when is 2 minus x square is equal to minus x. And this happens if and only if x square minus x minus 2 is equal to 0, and this happens if and only if x equal to 2 or x equal to minus 1. So of course this point is given by x equal to 2. Okay, the first coordinate is 2 that we know. We will determine the second coordinate in just a moment. And here we know that the first coordinate is minus 1. So now it is easy. So we know that this point also lie on the line y equal to minus x. So this point is given by the y coordinate of this point is given by minus 2, so which is the negative of the x coordinate, and of course this point is given by plus 1, which is the negative of the x coordinate. And we should figure out which is, so pictorially it is quite clear that the parabola lies above the line y equal to minus x, but algebraically we should be able to prove it. So even from this equation, let us try to see when is 2x minus x squared is bigger than or equal to, so when is 2x minus x squared is big, so not 2x minus x squared, so when is 2 minus x squared is bigger than or equal to minus x. So 2 minus x squared is bigger than or equal to minus x if and only if x squared minus x minus 2 is less than or equal to 0. So we have changed side, and this tells us that x minus 2 times x plus 1 is less than or equal to 0. And if you analyze this carefully, I am sure that you have had opportunity to do such things in your calculus 1 course. You will see that this happens if and only if x lies between minus 1 and 2. So indeed we are in a good shape. We see that the parabola lies above the line. So we want to compute our g minus f. So what is our g here? G is the function which is bigger in our notation. So we will call this function gx, we will call this function fx, and we will simply compute the area of our g minus f. So and how do we do this? So this is simply integral, so x equal to minus 1 here and x equal to 2 here. So we are going from minus 1 to 2. So we are going to do gx minus fx dx. So this turns out to be equal to integral from minus 1 to 2 minus x square minus x, and if you do your computations correctly, the answer will turn out to be equal to 9 by 2. So 9 by 2 square units to be very precise. So again, this was a very good situation. So here we can easily or sort of easily compute the area whenever we can compute the integral of g minus x in the region that we are looking at. But again, what if we do not have the luxury of this very nice inequality that one function is always bigger than or equal to another function in our interval? So let us have a look. So suppose we are given such a situation, so where the white line is represented by the function by the equation y equal to fx, and the yellow graph is given by the function y equal to gx. And for the sake of convenience, I have taken these two functions to be continuous functions. And suppose we are looking at the interval x equal to a, x equal to b, and suppose we want to compute this region. So suppose I call my whole region R. I call the first region R1, the second region R2, the third region R3. So what we do is the following. So we can see that in the situation when we are considering the region R1, here fx is bigger than or equal to gx, but in the second region the situation changes, and here we have fx less than or equal to gx. And again back to the third region, we are back to this case when fx is bigger than or equal to gx. But in each of the cases we know how do we compute these areas. So our idea is that we compute the area of the individual subregions and add them up. So for example, in this region, if I take the freedom of calling these 2 points, let's say, what do I call? So suppose I call it C and D. So the area of the whole region, so area of R is equal to area of R1 plus area of R2 plus area of R3, and we know how to compute these areas. So the first area is given by integral of f minus g, because here f is bigger than or equal to gx. So here we go from a to c plus integral c to d, and here we know that gx is bigger than or equal to fx. So g minus f of x dx, and in the last sub interval we are back in this case when f is bigger than or equal to g. So this is nothing but d to b f minus g x dx. So what we have exactly done is depicted in this small prose above the picture, which I encourage you to read when you go through the slides. So before we finish this, let me work out a proper example. So here is the example that I have chosen, and this comes in the Thomas's calculus book as an exercise. So it might not be fruitful to point out exactly which exercise is this, because the exercise numbers may change from editions to editions. Okay, so suppose we are given these two functions, two functions, y equal to x square minus 4 and y equal to minus x square minus 2x. And suppose we want to know the area which is bounded by these two curves, which is given by y equal to x square minus 4 and y equal to minus x square minus 2x, and in the region when x belongs to the closed interval minus 3 to 1. So again, it will be fruitful to actually compute the point of intersections of these two curves. So let us try to do it. So the functions that we have are given by y equal to x square minus 4, y equal to minus x square minus 2x. So let us use some sort of a fancy notation to understand also which curve is above which curve at what region. So I do not encourage you to do this at your exam or any formal setting, but this is for our purpose of the class. So x square minus 4 is bigger than, equal to, or less than minus x square minus 2x. So we will just preserve the sign. So here we will get 2x square plus 2x minus 4 is having the same relationship with 0, and then we can divide the whole inequality by 2. We will get x square plus x minus 2 is either bigger than or equal to 0 or less than equal to 0, and this happens if and only if x plus 2 times x minus 1 has the same relationship. Okay, so then from this set of inequality that we have just worked out, we have seen that x square minus 4 is bigger than minus x square minus 2x, or bigger than or equal to, if and only if so x is bigger than or equal to 1, or x is less than equal to minus 2, which is of course given in this picture. As you can see that when x is okay, so this point will turn out to be equal to 2. We will see in just a moment. So when is x square minus 4 equal to minus x square minus 2x? So this is if and only if when this is equal to 0. So either x equal to minus 2 or x equal to 1. So this point where the two curves intersect, the x coordinate is equal to 1. And what is this point? Let me determine in a moment. And this point is x equal to minus 2. So, and we are also asked to find the region from -3 to 1. So this is one of our lines, and x equal to 3 will be somewhere here, and we will try to calculate this in a moment. So x equal to 3. So what we are interested in is to compute the area of this region. So this is x equal to -3. Now you can see that from our picture, when x is bigger than 1, then the white graph goes below the yellow graph, which signifies that this function x square minus 4, or this function is smaller, so that is x square minus 4 is bigger. So this is what is signified by this inequality, and of course these are the point of intersection. Also, let me put it here for the convenience that x square minus 4 is less than minus x square minus 2x if and only if so the complementary region, which is somewhere in between when x lies in the interval. So if I put it less than or equal to here, it will turn out to be -2 and 1. And now it is a matter of integrating these two things, and let me just give you the idea. So let me first try to give names to these functions. So let me call the first function g1x, g2x. So if we are going to find the area of the region R, then we need to find the area of this region R1, and of course this region R2. So this is equal to area of R1 plus area of R2. And to compute R1, the area of the region R1, what we have to do, we have to look at which function is bigger here, and we have seen that the yellow graph lies above the white graph. So that means that this function y equal to x square minus 4 is bigger. So here we have to do this integration from -3 to -2, and so we have to -3 to -2, and we have to take this function x square minus 4, which of course is bigger here as we have just pointed out, minus of minus x square minus 2x dx plus the area of this region, so which is given by -2 to 1. So here we will change the order in which they will appear. So minus x square minus 2x and minus of x square minus 4 dx. And if you calculate this integral correctly, you will see that this integral will turn out to be equal to 38 by 3. So what have we shown? That the area of the region which is shaded in green is equal to 38 by 3 square units. So we will look at more applications in our later videos.